All right, welcome back. I have one more problem here for a central impact example. We've got A and B. They're both traveling to the right this time, and the coefficient of restitution is 0.6. So it is not perfectly plastic, and it is not perfectly elastic. It's somewhere in the middle. The masses are different, 100 grams and 300 grams, and the velocities are different. So to get started, let's write the conservation of momentum equation, which is ma va1 plus mb vb1, so that's the momentum before impact, and we have ma va2 plus mb vb2 for the momentum after impact. So we can fill out a lot of these values. ma is 100 grams, so it's 0.1 kilograms times 1.5 meters per second, plus the mass of B is 300 grams, so that's 0.3 kilograms, times its velocity, which is positive 0.2 meters per second. Both of the velocities are positive because they're both going to the right. We can even define the right as our positive direction. And then we can just write in our masses, so we have 0.1 kilograms times VA2 plus 0.3 kilograms times VB2. Okay, so the left-hand side simplifies to 0.21 kilogram meters per second, and the right side stays the same. And just notice before we go on that, again, we have units here on the left-hand side, kilogram meters per second. That is the units of momentum, and we have calculated the momentum before impact of the system to be 0.21 kilogram meters per second. It's positive, so that is oriented to the right. We're going to come back later in the problem and check that what we get for momentum after, depending on the velocities that we get, is actually the same as that. But our next step now is to write the equation for the coefficient of restitution, which is E, the coefficient of restitution itself, is equal to VB2 minus VA2. That's the relative velocity of the objects after impact on separation, divided by the relative velocity on approach, so VA1 minus VB1. While you're studying this stuff, you should memorize this equation. It will really, really help you. Now, we were given that the coefficient of restitution is equal to 0.6 in this problem, so we can fill that in. VB2 and VA2 are still unknowns, and then VA1, we have these guys, so that is 1.5 meters per second minus 0.2 meters per second. So on the bottom here we have 1.5 minus 0.2, so that is 1.3 meters per second. The relative velocity of the ball is just before impact, and you can always look back here and check to make sure that makes sense. VA is approaching quicker than VB, but 1.5 minus 0.2, 1.3, that does check out. What we want to do is we want to multiply 1.3 by both sides. So we're going to be left with, on the left-hand side, 0.78 meters per second is equal to the numerator of the previous fraction, which is VB2 minus VA2. I find it helpful to isolate one of the variables. Let's do it for VB2 here. So VB2 is equal to 0.78 meters per second plus VA2. So now what we're going to do is we're just going to take VB2 and we're just going to plug it right in here. We're going to substitute it into this equation. So everything stays the same up until that point, and we can just plug in everything that we had. So it's 0.78 meters per second plus VA2. There's kilograms in every term, so those will all drop out, and then we can simplify this to get VA2 is equal to negative 0.06 meters per second. And again, the negative sign indicates that it is going to the left. So we can put a box around this. This is the first part of our answer, VA2, and then we just have to plug it back in right here to this guy. So we have VB2 is equal to 0.78 meters per second plus negative 0.06 meters per second, and that gives us a value of VB2 of positive 0.72 meters per second, and that positive indicates it's going that way. So let's drop a box around that one as well. That is the other half of the answer that we're looking for, which is the velocity after impact of each object A and B. Now, if you're at this point, you've got the answer and you're on a test or a homework or something like that, and you have time, I really recommend checking that you get the same momentum for after impact using these velocities as you did for before impact. So we just want to plug these in to this expression here, ma va2 and mb vb2. We can do it in red here for momentum after. So we have 0.1 kilograms times negative 0.06 meters per second plus 0.3 kilograms times 0.72 meters per second. That gives us a value of negative 0.006 plus 0.216, which equals 0.21 kilogram meters per second, which is great. That's exactly what we had for momentum before, which equals what we have for momentum after. And because we calculated that based on the velocities after impact that we found, we know that we've done it correctly.